right, ladies and gentlemen, class recording has started. So, as I told you guys at the beginning of the week, one of the things that I really like about this unit is that we get to look at the broad spectrum of things that exist in our universe. This unit starts, in our discussion, deals with the very, very smallest things we know of, the nucleus of an atom, and what goes on in the nucleus of that atom, and the kind of changes that occur, and what possibly can happen because of those changes. But we find out that those changes that occur on that subatomic level, right, the nucleus is subatomic, smaller than an atom, have a huge impact on the functioning of our universe as a whole. So now we fast forward from the smallest part of the spectrum all the way to the biggest part of the spectrum, and we talk about stars. So first, I'm sure you're all, you've heard of a star, but what is it? So what is a star? Go ahead. Gas. Actually, that's kind of right, but not totally right. Based on our discussion from earlier, a couple units ago, we talked about states of matter. A lot of stars actually aren't gas. They're plasma, because they're not actually in the form of atoms. It's too hot for them actually to be in the form of atoms. But they do get fused together into smaller nuclei. So a star is a huge collection of plasma and very hot gas. So it's not just gas, because sometimes it's not atomic, right? It's just pieces, parts, protons, electrons, neutrons, just kind of, but they get fused together, all right? So, huge collection of plasma and very hot gas. Stars emit light and other types of electromagnetic radiation during the process of fusion. Stars work on the process of fusion, and we'll talk about that more on Monday when we talk about the life cycle. How does a star begin? But, like we discussed earlier, right, E equals mc squared. During that process of fusion, some mass is converted into energy, and when that mass is converted into energy, that energy radiates, right? We give it off in the form of electromagnetic radiation, electromagnetic waves. Some of it's visible light, but a lot of times it's other types of electromagnetic radiation, radio waves, X-rays, gamma rays, all those different kinds. All right, good there? While stars are very prominent in our universe, they are spread apart, especially, in some cases more than others. We're very close to a star, right? We're very close to the sun, but we are very, very far away from all the other stars that are out there. Sometimes hundreds and billions of years away from those stars. So because there's so much empty space and the distances are so great, we have to come up with some ways to express those differences, maybe in a little more convenient form. So, the first one we talk about is a light year. Okay? As its name suggests, now its name is a little confusing. A light year is not a time measurement. A light year is a distance measurement. The distance that light travels in 1 year. Do we remember the speed at which light travels from our discussion earlier? 186,000 miles per second, or 300 million meters per second. This is light going that fast for an entire year. So 300 million meters every second for a whole year. That is 1 light year. It's a distance. Now, okay, fine. Consider, though, that the closest star to us, other than the sun, is 4.3 light years away. That's the closest other star. Light traveling at 300 million meters every second for 4 1/3 years. It just, to me, every time we talk about it, it's just like blows my mind how far apart these things are. So, that being said, right, that sort of limits our ability to study those stars, at least up close. So we have to look at other ways that we can look at them and figure out things about them, and we'll get into that a little bit more. Right? So we know that these distances, but what does that do for us? Well, we want to start locating these stars and figuring out how do we know that that star is 4.3 light years away? Well, when we look at the stars, we use something called parallax. Right? Anybody hunt? Hunters out there? Anybody ever shot a gun before? Like target practice, anything like that? Okay. Are we familiar with the concept, like those of you that have shot a gun before, are you familiar, you have like a dominant eye and like a recessive eye, like one eye is better than the other eye? So, with that being said, take this, okay, so take your thumb, put it out like this, okay, and then close one eye, okay? And then put your thumb over something, right? Like there's the dinosaur in the cars up there, if you want to like cover up that with your thumb, okay? So now, switch eyes, right? Right? Come on, Eris.
I can't close this eye.
Okay, sorry. So, if you switch eyes, right, sometimes the car is covered up, sometimes it's not, right? Based on where you look at it from. That's sort of how our eyes... That's sort of how our eyes work. That's why we have such good vision, because we have two eyes. And because we look at things from different vantage points, this eye looks at it from here, this eye looks at it from here, our brain takes information from both of those eyes, puts it together, and goes, oh, this is closer to me than that. This is closer to me than that. It allows us to have depth perception. That's one of the ways that we figure out how far away these stars are. That where we look at the stars from determines where they show up. Just like where your thumb appears depends on which eye you look out of. As far as stars go, right, as the Earth moves in its orbit, scientists look at stars from different angles. Because sometimes we're on one side of the sun, and sometimes we're on the other side of the sun. And that means we look at stars from different positions. And that causes them to look at different places or appear to be in different places in the sky at certain parts of the year versus other parts of the year. And you guys have this picture in your notes, right? Here's Earth in January, here's Earth in July. Here's a star. If we look at it, just like your thumb, right, that star moves. When we're looking at it in the winter, and then we're looking at it in the summer. So, if we draw a line from this, where we are in the winter to that star, and we draw a line to where we are in the summer to that star, the intersection of the lines is where the star actually is. We know this distance, right? We know the diameter of our orbit, so now we've basically made a triangle, right, where we know one of the sides. And if you have a triangle where you know one of the sides, you can figure out the other sides, right? You can figure out the height of the triangle and all those fun things that you're learning in geometry and all that stuff, and bisect it and whatever you want to do with it, right? Okay. But based on that, we can then figure out how far away those stars are by how much they move in their apparent position. Stars that are closer to us will show a greater parallax. Just like if you move your thumb closer to your eye, its apparent position moves more than if your thumb is way out on the end of your arm. Right? How much it moves depends on how close it is, or the degree of parallax depends on the distance away from Earth. Good there. Okay, now that we know how far away these stars are, we got to look at some other factors to start categorizing them, to start characterizing them as one different from the other. So there's lots of things that we look at. All right, first, color and temperature. I'm sure you guys have probably noticed before that if you look at certain stars, they look different colors. Not that they, one's green and one's blue and one's orange, but they have like a tint to them, right? There's certain stars that are red, there's certain stars that are more blue, there's certain stars that are more white, depending on, different factors. That color that they appear is dependent upon the temperature of the star. The temperature of a flame can be estimated by the color of that flame. You'll learn this a little bit more in chemistry when you start looking at absorption spectrum and things like that. The color of the stars can be used to determine their relative temperatures. they're all really, really hot. They're all giving off tons of energy, but some of them give off more energy than others, right? The hottest stars will appear blue. Those stars, blue, and then the ones that are really, really hot are like bluish white, right? We're talking about stars that have temperatures over 30,000 Kelvin, right? Kelvin being an absolute temperature scale that starts at absolute 0 and goes upward, right? Medium stars appear yellow. Those are the stars in the 5,000 to 6,000 Kelvin range. That's still hot enough to melt and vaporize anything here on Earth, but relatively speaking, according to related to other stars, not really that hot. And then our coolest stars have more of a reddish tint to them. They're in the 3,000 Kelvin range. Again, still hot enough to melt and vaporize anything here on Earth, but relatively speaking, not as hot as some of those other stars. Okay? Our star, right? We'll find this out as we go along here. That our sun is sickeningly average. It's like right down the middle of every single categorization of stars that are out there. It's like sickening how average it really is. But it's important to us. But in the big picture, nah.
I'm fine with it.
It's like C+, baby. It's just like, you know. So. All right. So, brightness. Brightness is another way that we categorize that. But brightness can be a little misleading because brightness depends on a couple of things. Closer stars appear brighter. On that last chart that I just showed you, right, our sun is, by comparison, not very hot according to others, or when compared to other stars. But it is by far the brightest thing in our sky, right? So brightness can't just be related to the temperature of that star or how much energy it's giving off because, right, our sun doesn't give off that much energy, relatively speaking, but it's still by far the brightest thing in our sky, right? So brightness depends on how close we are, but it also depends on how much energy it's giving off, right? The sun versus other stars, right? Apparent brightness is the brightness of the star as it appears on Earth. And that's what we see, but not always a good judge of that star in relation to other stars, right? If we judged all stars just based on what they looked like from Earth, our sun would be the most awesome star in the universe, right? Not that it's not great, but, you know, it's just not, when compared to all the other stars, right? So apparent brightness versus absolute brightness. How bright that star actually is based on not how it looks to us, but how much energy it's actually giving off. That's how we can compare apples to apples when we're talking about our star compared to other stars. Right? So apparent brightness, how bright is it to us, versus absolute brightness, if we lined them all up together, how bright would they be? Illustrated by this picture, right? So if you're at a park and you have a row of these street lights, right? The one that's closer to you is obviously going to appear brighter to you, right? But that doesn't mean it's the brightest light out of the whole row. It's just because it's closer to you, right? So apparent brightness versus absolute brightness. Good there? All right. Let's do this part next. We'll finish up these last couple, and then let's get through size and mass and hopefully composition, and then we'll do HR diagram on Monday. So size and mass, right? Once we know the temperature and the absolute brightness, the diameter and the volume can be estimated because we know how hot it is, we know how bright it is, we know how much energy it's giving off. That energy has to come from mass. So we can do a calculation to figure out, okay, well, how big is that star actually, right? The mass of the star can be estimated also by observing the gravitational effects it has on the objects around it. If somebody's looking at our solar system, they can see that our star has a bunch of rocks floating around it, right, or orbiting around it. And based on how fast those rocks orbit, that we call planets, right, all of them aren't rocks, some of them are gas, right, we can figure out how big that star is because of the amount of gravity that is exerting on other objects. Okay? So not only how much does it appear, but also what is it doing to stuff around it. Okay? And then, let's finish this up. Composition, what is it made out of? Okay? We'll finish this on Monday, that's fine. We'll finish it up. All right, so the Mars lab, right? If you want to do it, great, turn it in. If you don't want to do it, no harm done, and we move on with our lives. So, okay. Yes?
If we turn in late, do we get points off?
No.